Okay, hello everyone. The goal of this small session is to review some of the problems as I promised you. So the first thing I will review quickly are the two questions that one of your classmates asked. Is about determinant. And the problem he asked were number 20 and number 24 in section 2.3.2. Okay. Now, number 20 is based on the effect of determinant on elementary row operation. So I will review quickly what their effect. So the effect is I do it for 2 by 2 matrix and then everything follow for 3 by 3 or 4 by 4. So the first effect, if I take one row, so I have initially a matrix A, B, C, D. I take one row, and that's crucial, one row or one column, and I multiply it by a constant, k. So one row, not both. If I multiply one row, the effect on the determinant is that we can take the k out. So that's the first property. Now, if we switch two rows or two columns, then the determinant is multiplied by a negative number. That's the second operation. Now, the third operation, which is the one that we use the most, is the following. If we perform the following operation on the determinant, we take a row, let me call it Ri, I multiply it by a constant, k, and then I add it to a row Rj, and whatever I get will become my new Rj. So this is a little bit tricky. So whatever I have here should be here, and that's important. So if I have minus Rj, this fails. It has to be plus Rj, and that would be Rj. Then the determinant will not be affected at all. So in terms of a 2 by 2 matrix, this would become the following. So if I take the determinant of A, B, C, D, and let us say I perform the following operation on it, and that's an equal sign here. I take the first row, multiply it by k, add it to the second, and this will become my second row. So let us see what does this mean. It means I did not touch the first. I multiply the first by a k, add it to the second, and that's kb plus d. If I do this operation, there is equality. It means the determinant is not changed at all. Okay, so these are the effect of elementary row operation on a matrix. So with this in mind, I will look at number 20 in the book. Use the pencil. And the problem is the following. I have an initial matrix, ABC, DEF, GHI. And the determinant of this matrix is 7. So number 20 tells me take the following matrix, A, B, C, and D plus 3G, E plus 3H, and F plus 3I. And finally here it will give me GHI. And they want me to find the determinant of this matrix. So now if we look very carefully here, if I take the third row, and I multiply it by -3, add it to the second. So I'm still here. And this will become my second row. So this one should not be changed. This should be exactly that one. This operation will not affect the determinant. And why did I do that? Because if I do this operation, so I do not touch the last row, this is not being touched at all, it's the third row. I'm going to multiply this by -3 and add it. This will give me a D. -3 added will give me the E. -3 added, this will give me the F. And this is based on the previous problem. That's exactly equal to 7. Okay, so actually the determinant hasn't changed at all. All right, so that will be number 20. I strongly advise you at this stage to look at number 19. You guys do it. Make sure you get the right answer. All right, the other question that I one of you addressed in the section of determinant is the following. It's number 24. Okay, and number 24 is based on the following idea. So if I have a matrix A, and let me say that it's column RA1 through AN, then we have the following equivalence. A invertible, the matrix A is invertible. It's equivalent to say that the columns of A are linearly independent. Equivalent to say the determinant is different from 0. So if you have a matrix n by n, if its determinant is not 0, we can immediately conclude that the columns are linearly independent, because determinant non-zero give me also the invertibility. So number 24 is actually this problem. So I have a bunch of vectors. So it's 4, 6, 2. And so that's my A1 if you want. And I have my other vector minus 7, 0, 1. I meant minus 7, 0, 7. And that's my A2. And I have minus 3, minus 5, minus 2. And that's my A3. So I have the 3 vector, and the problem is very clear. Use determinant to decide if they are linearly independent. And so the idea is I'm going to take the matrix A, whose column are 4, 6, 2, minus 7, 0, 7, minus 3, minus 5, and minus 2. And I'm going to check the determinant of this matrix. So if the determinant is 0, the columns are linearly dependent. Determinant not 0, the columns are linearly independent. So I just compute the determinant of A. That is 3 by 3. And minus 2. So I see this is equal to 1. That's a simple determinant. I would like to do cofactor across the third row. So the second row, cofactor across the second row. So I can take my checkerboard sign. So that's a minus, that's a plus, that's a minus. And then I compute the determinant. I'm going to have minus 6 times the determinant of this matrix, minus 7, 7, minus 3, 2, plus 0 times something, we don't care, and then minus, minus, plus 5 times the determinant of what's left, which is a 4, it's a 2, it's a minus 7, and it is a 7. Okay, so finally I'm going to get a number. So minus 6 times minus 14 plus 21 plus 5 times 28 plus 14. And then we pick up our calculator and we compute those numbers. So I will get 21 minus 14 times is 6. So that's going to give me a minus 42. And this giving me 28 plus 14 times 5. Unless I'm doing any slight stupid mistake here. So it's a minus 6, minus 7, 7, minus 3, and that's a minus 2. That's what my mistake is. So that's going to give me minus 14 minus minus. Going to give me plus 14. And this is going to give me 14 plus 21. So plus 21 times is 6. So it's going to give me minus 210. And this is giving me 28 plus 14 times 5 plus 210. So this is giving me equal to 0. Since the determinant equal to 0, it means the columns are linearly dependent. The columns are linearly dependent. Okay, so that's for determinant. you still have to review. So that's the question you ask about determinant. What you have to review, of course, you should review what I did in the first problem, number 20. Make sure you know how to compute the determinant. Make sure you know the relationship between invertibility and the column of the invertibility, the determinant, and the linear dependence of the column. And then the last thing you should know is all the property of the determinant. It means determinant of the product is product of the determinant. Determinant of the inverse is 1 over determinant of A. So make sure you do basically number 39. So make sure to review, because I did that in class. Make sure also to review number 39 in section 3.2. Okay, and make sure you can compute determinant. You will be asked directly to compute determinant. All right, so this will take care of the determinant. Now, what other part, what you guys are responsible for? Of course, everything is very clear here. What you should know, first, linear transformation, and I will go over the problem that I gave on my exam last year to review that slightly. What's the linear transformation? What's the word range mean? How to interpret linearity geometrically? How to show that a transformation is not linear? And actually, I gave you 2 problems to help you with the review, and I've done this in class, so you guys review them. The fact that any transformation given by a matrix, where a matrix have constant entry times x, so every transformation that given by this rule is automatically a linear transformation. How to find the standard matrix of a linear transformation, whether the transformation is given algebraically, geometrically, what's the rotation matrix, and here I'm telling you review the problem is signed. And recall that the matrix is linear, then the standard matrix is given by what T does to E1, E2, and En. So very briefly, I'll go over the questions in my previous exam that has to do with linearity of a transformation. So basically, transformation is linear. It means it has the following true property. That's linearity. And those 2 properties, I can get the C out. That's linearity. Now, any transformation given by the rule, A times X, where A is a matrix with constant entry, then T is linear. So if this is the rule, then it is linear. Now, example of nonlinear, there are a lot of nonlinear transformation. So let us say I give you a transformation. Suppose there are a lot of them. This is example of nonlinear. I can square that and I can add 2. This is the example not linear. How you show not linear? To show it's not linear, you give me example of a C. Like for example, you can take C equal to 2. And you give me example of a vector. Like in this case, I'm going to take 1, 2. And you show me, you convince me that if you compute T of U, you will not get twice. You cannot remove that. So that's how you show nonlinearity. Okay. And now, 2 things, the range. The range are the output value. So let's review quickly the word range. The range is an output value. So it means if I have a transformation from here to here, so this is Rn, this is Rm. So a vector here is in the range if I can find a vector x, an input vector, such that T of x equal to B. That's what means in the range. Okay, so with this in mind, I will review the problem I've assigned in my old exam that has to be related to the range. And this helps us to remember that. So, and you guys have the solution. This is just a quick review. So number 12 addresses this issue. So I will go over it very quickly. So I have this transformation, x1, x2, x3, and this is the output. That's the input, that's the output. That's how you understand it. The input is a vector in R3. The output is a vector in R4, input, output. Find the standard matrix of T. So to answer this question, so the standard matrix is basically T of E1, T of E2, T of E3, because I am the input is in R3, you can either compute those or by inspection. You ask yourself, this is the output. How can I write this as a matrix times a vector? So this is really by simple inspection. You realize, I can take 1, 0, 1, 0, 1, 0, 0, minus 1, 1, minus 1, 0, 1. So you can do that by inspection, or you can use the formula itself. It doesn't really matter how you do it. You get exactly the same answer. Now, is the vector 1, 2, 0, 3 in the range? So just remember, the range, it means an output value. So here I have a function from R3 to R4. So my input is in R3. So my input, 3 numbers, my output, 4 entries. So I'm giving you a vector here. I'm telling you, is it in the range? It means, can you find a vector in R3 that T will take to be? That's really what the question is. So the question is, we need to check if we can find X. And always we have to remember, what is my X? In R3, it means I'm an input vector whose output is 1, 2, 0, 3. It means, can I find the X such that T of X? But this is what T of X is. Either this, if you want, or that. This is the same thing, such that A times X equal 1, 2, 0, 3, where A is my standard matrix. So it's really boiling down to solve a system. X1 plus X3 equal to 1, X2 equal to 2, minus X2 plus X3 equals 0, and so on and so forth. So it's really boiling down to solve a system. So we solve it, as we always solve. We set up the augmented matrix, and we solve. So remember, I'm looking for the input, which is being sent to 1, 2, 0, 3. So we solve, you guys do all that, and then after we solve, we get to this augmented. Every time you need to solve, you have to take the augmented matrix. That's how we solve now, and that's how you guys should be solving later on. Now, immediately we realize that's a consistent system because I don't have 0, 0, 0, non-zero down there. So it's a consistent. It means that the vector is in the range. What does it mean in the range? It means if we actually solve this system, you're going to get a vector X in R2. That's the input vector, whose output is 1, 2, 0, 3. So that's really what it means. I can actually give you a specific vector, which output is 1, 2, 0, 3. Now, my second question is every vector in the range? I really don't know. It means if I pick an arbitrary vector here, can I always find an input that's being sent to it? So basically, this is equivalent to ask this question. Does T of X equal B1 has a solution for all B? It means regardless which output vector here, can I always find something that goes to it? That's really what my question is. So I'm going to do the same thing as before, but now I'm going to put any B1, B2. So we do that. So we try to solve, and we solve, and we solve very carefully. And we stop when we hit the echelon form. So I stopped right here. So what did I get here? I have 0, 0, 0. But now I cannot find a solution for all B. I can find only solution for the vector B1, B2, B3 that satisfy the condition this is equal to 0. Otherwise, I will have inconsistency. So it's in the range only under this condition. So for example, if I pick a vector that does not satisfy this condition, it will not be in the range. So I put a vector, and I say it's not in the range. So the answer is the question is definitely a no. Okay, that's a quick review of the range. All right, the two other problems from the old exam that actually relevant to the this idea are the following. I gave you a matrix, and it's an linear transformation. It's a geometric, and I tell you it does the following two. It takes a vector, deflected through the x1 axis. So I'm telling you it's linear, so you don't have to worry about that. And then I tell you it rotates by 2 pi over 3. And the question is, find the standard matrix. The standard matrix is always what the matrix does to E1, what the matrix does to E2. That's the standard matrix. So if you want to find it, so what does standard matrix is? Standard matrix means the following. We have never should lose track. It means if I find this, it means the way T acts on any vector, if I find the standard matrix, is simple. It takes the standard matrix I found times the vector. That's really what it does. So if I know, this is telling me if I know what it does to E1 and E2, I know what it does to any other vector I want. So how do we do that? We start with U1, which is 1, 0, and that's 1, 0. And what does the function do? First, it reflects. So I'm going to see what it does to E1. It reflects E1 across the X1 axis. That's the X1 axis. Reflecting across the X1 axis is not really going to do anything to it. So it stays 1, 0. And then what T does? It rotates. So it takes this one and rotates it by 2 pi over 3. So we land here. But what is this vector? How do we get a rotation? To get a vector, if we take a vector and we rotate it, to find the answer, we multiply it by the rotation matrix. And the rotation matrix is cosine theta, sine theta, minus sine theta, cosine theta. So I take it multiplied by the rotation matrix, I get this vector here. And that would be T of E1. I'll do verbatim the same thing for E2. So I start with E2, I reflect it. So this is now E2. E2 right here. When I reflect it, I'm going to land there. So that's 0, minus 1. And it's this vector I'm going to rotate. I ask myself where I'm going to land. So to find where I rotate when I'm landing, I have to multiply it by the rotation matrix. So I'm multiplying by the rotation matrix that you should memorize or you look up. But usually a lot of students, because it was face-to-face class, they memorize the rotation matrix. So I multiplied those 0 times, yeah, this is correct. And that is 0 times minus half, I got that. Means my standard matrix is T of E1, T of E2. T of E1 is this vector, T of E2 is that vector. So this is just a little bit to tell you how to find the standard matrix if in case the problem is done geometrically. Now the last problem I gave on that particular exam that has to do with linearity as well. And this will close linearity is the following. So I give them a function from R2 to R2. It's a linear. So I'm giving them to a linear. And then I told them, okay, it takes the vector 10, 20 to 2, 7 and 1, 1 to 5, 6. Okay, find T of 3, 4, 6, 4. So this is a really kind of weird question because I'm not giving you E1 and I'm not giving you E2. So you don't know what T does to E1 and you don't know what T does to E2. So, but how can we still find what T does to any vector? And I give you a hint. The only way you can do it is take 34, 64 and write it as a linear combination of those two vectors. So that was my hint. And let's see why I gave you this hint. All right, so first I start by doing this. So I write this vector as a linear combination. It means I look for scalar S and R such that my vector is S times that plus R times this. So that's a simple problem that we've done a lot for. You set up your matrix and you find your scalars, your weights. Okay, so I realized that 34, 64, it could be written 3 times that plus 4 times this. You can even spot it and look at this answer. What does this mean? And why did I give you the hint? Because how does linearity do? I know what T does to this vector, and I know what T does to this vector. 34, 64 is a linear combination. So T of that vector is, we're using the property of linearity. T of CU plus TV is actually C times T of U plus T times T of V. That's the property we are using. And that's exactly what I did. So it's 3 times T of this vector plus 4 times T of that. So basically it's 3 times 2, 7 plus 4 times 5, 6, which is give me that vector. So it's another application for linearity. All right, so let's take care of the first idea of the exam, linear transformation, and we took care of the determinant. Now algebra of matrices, inverse of matrix. Okay, absolutely crucial to know how to multiply matrices, how to add them, when can we add them, how to find the transpose of a matrix, and what are the properties of the operation, namely the product. And the main thing about the product is that that you cannot flip those. This is not BA, and this causes a lot of problems. Now for the inverse, you have to know exactly how to find the inverse, and that's the algorithm we will be using. I know that Professor Tarfolea talked about another way to find the inverse that use the adjoint matrix, but that's the one I want you to use for the exam. How to use the inverse to solve a system, and then the property of the inverse, which I tell you exactly which one. So property, and maybe the one that give us a difficulty, that inverse of that is B inverse A inverse. That's Remember that? And if you multiply a matrix by a scalar and you invert it, it's 1 over C times the inverse of A. So we have to be very careful with that. So I will go very quickly over some of the problems I've assigned on my previous exam, and you guys have them, that has to deal a little bit with the algebra of matrices. And I will make comments about some stuff. I think I gave you this as a quiz before. So here you have two matrices A and B, and you have a matrix C. And the question is, let X be a 2 by 2 matrix that satisfies this equation. I want you to find X. The easiest way to do this problem is basically first to solve for X. So when I give you this as a quiz, the student, I mean, not bad, they tried to write for X some entries and solve for them. It's easier to solve for X. So A times X plus B equal to C. It means A times X is C minus B. Now, here is where a lot of you did a mistake. And this is important. And since A is invertible, I solved for X. And this is where the mistake that you guys have done. Because matrices don't have these properties. Some students just knew that they have to multiply by the inverse, but they didn't know how to multiply by A inverse. So if a student to write something like that, so a lot actually, on their quiz, they wrote stuff like this. So they multiplied from the right. This has got me nowhere, because A times X times A inverse is not X, because I cannot switch X A inverse with A inverse X. So this is not X. So if the student multiplied from the right, get me nowhere. So this is absolutely wrong. The only way we can eliminate this A is multiplying from the left by A inverse. So I have to multiply here by A inverse. So X is A inverse times C minus B. A lot of students did this mistake, and that's absolutely wrong. So once you do that, the rest is simple. A inverse, you can compute it using either the algorithm AI, I inverse, or if A is A, B, C, D, we learned a very simple algorithm to compute it. So it's 1 over AD minus BC. Those are switched. Along the diagonal will be switched. Off the diagonal are multiplied by negative. So you can either use the algorithm AI, rho equivalent to I, A inverse, or you can use the simple formula which work for a 2 by 2. Then the rest is simple. You guys can do the algebra. So that's really my main remark concerning this problem. Now, number 8 is again more of the same thing. It's just algebra of matrices. So I gave you two matrices, or I gave them two matrices, but I gave them this specific property. I told them this should be satisfied and this should be satisfied, because usually this is not true. So I thought, okay, suppose you have two matrices A, B1 and A, B1 and B2, such that A commute with B1 and A commute with B2. When can this occur? Under what condition on the matrix? Because this is not true in general. So the problem was simple. We said AB1 equal B1A. This is AB1 and that's B1A. I multiplied them, I set them equal. I said, okay, when can this happen? All right, two matrices are equal if they have the same entry. So this will happen when B is 0 and C is 0. So those have to be 0. So you realize this doesn't happen all the time. And then I did exactly for B2, and AB2 equal B2A. I said AB2 equal B2A. I said, okay, when does this occur? This occur when A, okay, that should be a mistake. 0, 0, A plus B, 0, 0, and this should be a 0. So I have a slight mistake over there. That should be a 0. So this should occur when A equal to D. So when we have those two properties satisfied, when B equals C equals 0 and A equal to D, it means A should have this following format. All right, and this is like interesting because I'm telling you that usually it doesn't commute. If it commute, the only way it can commute if A have this very specific format, so it doesn't commute in general. All right, so that is the algebra of matrices. And then number 10, I will not go over it. This is just a matter of computing the inverse. And the algorithm, so I gave you a matrix, find the inverse. First, immediately the matrix is invertible because I have a pivot in every row, in every column. Or you can compute the determinant. And in this particular scenario, the determinant is 1, because if a matrix is triangular, The determinant is the product of the terms along the diagonal. So the determinant here is 1. It means that the matrix is immediately invertible. And to compute the inverse, you just use the algorithm. So go over what I did verbatim. And if I put X, Y, and Z, which most probably I will on your exam, make sure that it shouldn't bother you. So you should be able to work with X, Y, Z, and A, right? Number 12 is just help you review all the properties of the algebra of matrices. First, AB squared, A squared, B squared, absolutely false. A minus B, A plus B is equal to that. Again, it's false because always the commutativity get into the picture. This problem is to review property of the inverse. And it tells you that this is false, even though it's B inverse, A inverse, but 2 has to be inverted. Make it false. A squared, the inverse of A squared is the square of A inverse. And that's true because if you take the inverse of A squared, it means the inverse of A times A. Now the property of inverse, then it's A inverse times A inverse, which give me A inverse squared. And then if AB equal AC, then B equal to C. That's true in false in general. It's true in this scenario because A is invertible. Otherwise, it's not necessarily true. Then this problem is actually to make sure you guys are not know your algebra. So are those equal? Okay, I don't know by looking at this. So I start working it out. A, B, C inverse, B, A inverse, you work it out. BC is C inverse, B inverse, times B, A inverse, which is equal to AC inverse. Those could be combined to give me an A. And this would leave me A, C inverse, A inverse. And I said at the beginning, this is not C inverse. I cannot flip those around. So cannot simplify any further. So those two problems represent a very good review of the algebra of matrices. And then we have the invertible matrix theorem that you should definitely be aware of. So invertible matrix theorem builds this relationship between a matrix invertible. It means all its, it has a pivot in every row. You can row reduce it to the identity. Its columns are linearly independent. The system AX equal to 0 have a unique solution. The system AX equal to B have a solution for all B. So that's really what the invertible matrix theorem is. So this is, if my memory is correct, it was like a problem to just make sure you guys know it. So I have an n by n matrix, and let us say that Bx equal to C is inconsistent, and that's crucial for some C. So you have this matrix, but the system Bx equal to C is constant. So there is a vector C such that Bx equal to C has no solution. And the question is, does the equation Bx equal to 0 has more than one solution? And my answer is true, because if Bx equal to C is inconsistent, it means when I'm solving BC, and I augment it, because we have inconsistency, it means somehow the echelon form at the end gonna have 0, 0, 0, and a non-zero term. But then B is the n by n matrix. If this row is all 0, it means we have at most n minus 1 pivot, because that's the n by n matrix, n minus 1 pivot. It means one of the columns does not have a pivot. It means that the system will have to have a free variable. So definitely Bx equal to 0 has one more solution. Now, does the column of B span Rn? Absolutely not, because if Bx equals C is inconsistent, it means the vector C itself cannot be written as a linear combination of the columns of B. Absolutely not. The matrix B has n pivot. Now, no, because that's the argument right there. The columns are linearly independent. Absolutely no, that's the argument also right there. Okay, so this is basically telling you if a matrix is not invertible, everything falls apart. It means the column will be dependent. It will have less than n pivot. The column will not span Rn. Bx equal to 0 will have more than one solution. So basically, if it's not invertible, all those will have. Okay, so this will carry us. So this is all about the invertible matrices. And then subspaces. I'll review very quickly subspace. And then a basis. So subspace, this will carry me, I guess. What did I give them for subspaces? Okay, here we are. So subspaces. Subspaces, it means collection. You have, suppose, a subspace of R3, let us say, because that's my question, are collections of vectors that have specific properties. So a bunch of vectors that has the property that whenever, so suppose H is a collection, and in class we gave a lot of those, and a subspace, if it has a zero vector in it, every time two vectors are in it, you add them, you create a new vector, it's also in H. It means whatever property that makes U in H and V in H will make the sum in H. And finally, if a vector in H and you scale it, it remains in H. So that's what the subspace is. And I give them a bunch of problems and I tell them are those subspaces. So the first question is, suppose H all the vector that satisfy this condition. So the third component is the first one squared plus x2. Okay, and the question is it a subspace? So it means all the conditions satisfied. First, the zero vector is in it because 0, 0, 0, I will have 0 is 0 squared plus 0. Now, is it closed under scalar multiplication? Usually it's easy to start with a scalar multiplication. If it works, then you move to addition. Is it closed? Actually, not, and I give you an example. Suppose I take the vector 2, 1, 5. Is it in H? So first I have to start with a vector in H to show it's not, and show you that if you scale it, you're not in H anymore. So I start with vector in H. It has to be here. And I say, yes, it is because the third component, 5, is 4 plus 1. So this is a vector in H. So it satisfied this condition. When I scaled it, so I took the scalar minus 1. You could have taken another scalar. I create a whole new vector. This whole new vector is not in H because it doesn't satisfy the condition. If I take the third component is minus 5, or if I take this one squared, I get a 4, minus 1 is going to give me 3 different from 5. So H is a bunch of vectors in R3. I don't know how to draw them, but I took a specific vector. This is my X. It satisfied, it is in H, but when I scaled it, it's not in H. So my H is not a subspace. Okay. So the other two problems I gave them, I take, okay, let H be all the vectors, x1, x2, x3, that satisfy this condition. So I'm taking very, very specific vectors here. I'm taking vectors that satisfy this condition. So for example, if I take this vector, so 5, or basically, suppose I take 2, 3, 5, that's satisfied. X3 is x1 plus x2, so that's in H. But the minute I take 2, 3, 4, definitely not in H. So H is specific vectors in R3, not all of them. And it is a subspace. Okay, first the zero vector is in it. And as I said, it's usually easier to start with the scalar. And so assume X is in H. It means this is satisfied. That's crucial. That's what it means in H. And I scale it. So I multiply by a scalar. So I'm creating a whole new vector. And the question is this new vector in H? It means does this new vector satisfy the condition? It means is the third component equal the sum of the first two? But then, you know, CX3 is equal to that because my starting vector is in H. It means this X3 is the sum of those two. It's already, this is satisfied. So it means CX3 is equal to CX1 plus CX2. It means the third is the first plus the second. Therefore, I am in my subspace. So it's closed under scalar. Now let's see, is it closed under addition? And it is, because I start with two vectors in H. It means my vector satisfies this condition. And now I create a third one, which is their sum. And the question is this new one satisfies it? So I take X3 plus Y3. And I said, you know, X3 satisfied this condition. It means it's X1 plus X2. Y3 satisfies it. It means Y1 plus Y2. So when I add them and I rearrange the term, I get the first component plus the second. Therefore, I am in H. Okay, that's a subspace. Now, finally, I take all the vectors that set X1 squared plus X2 squared plus X3 squared equal to 0. And definitely the zero vector is in it. And my remark here is that the only vector that satisfies this condition. If you take three numbers, this is positive, 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 because it's squared. You add them, you get 0. There is one way out. If each one of them is 0. So this is the only vector that satisfies this condition is actually the 0 vector. It means my H consists only of the 0 vector. Therefore, it is a subspace. Okay. So that's a quick review of the subspace. Now, basis of a subspace. Make sure you go over that idea of a basis. And in class, I gave a lot of example bases. You are responsible for a basis, as I said. So I will review the problem I assigned again last year concerning this topic. Okay. All right. So number 6 in here. And go over what I did in class. It's crucial. So in each part, find the value of A, if any, for which the given vectors will form a basis for R3. So in this problem, I'm taking my subspace equal to R3, and I'm giving you a bunch of vectors, and with a parameter A somewhere. I'm asking you, okay, is there any value of A which will make those vectors linearly a basis for R3? Remember, a basis for R3 are vectors in R3 that have satisfied two conditions. First, they have to be linearly independent. And second, they should cover R3. It means they are vectors such that everything in R3 should be their linear combination. So two conditions have to be satisfied. So here I have 4 vectors in R3. And they are different vectors. So now 2 could be the same. Regardless what A is, it's different from all the others. So do they form the basis? And my answer is, they do not form a basis regardless what the value of A is. Okay, and because vectors in a basis should be linearly independent. If you have 4 different vectors in R3, they are always linearly dependent. And this is something I've talked about it clearly in class. So 4 vectors in R3 are always linearly dependent. So no matter what plug in here for A, we do not form a basis. Part 2. I have 2 vectors. Do they form a basis? Again, I'm writing do not form a basis regardless of the value of A. They are linearly independent. Definitely. They cannot be obtained at scalar multiple. But the main condition, the other important, very important condition for basis is that the vectors should cover R3. It means everything in R3 should be their linear combination. And here we have 2 vectors. 2 vectors in R3. When I take their span, I'm just going to get a plane in R3. So do not form a basis regardless of A. Because vectors in a basis should span R3. It means every vector in R3 should be a linear combination of the vector. Every vector should be a linear combination. And the span of 2 vectors is nothing more than a plane. So geometrically not. Finally, I gave you 3 vectors. And the question is, do they form a basis? For which A form a basis? Now, 3 vectors are the best candidate. But to form a basis, they have to be linearly independent. But since I have an A in here, I do not know whether they are linearly independent or not. So I have to check. So the 3 vectors in R3 form a basis as long as they are linearly independent. If they are linearly independent, they will span immediately. So now my question is, for which A are they linearly independent? Okay, so we solve for linear independence. So I say, okay, and in a minute, I can show you another way to do this problem. Okay, so, okay, I solve C11A1, blah, 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 and I check for linear independence and I ask myself, for which value of A I have a unique solution, or for which value of A I have no free variable. So I start with the matrix, reduce it, and reduce it. And then I reach here, and then analyze. Those are linearly independent if we have a pivot in every column. That's what linear independence. But in this problem, I may not have a pivot in every column depending on the A. So here I will have a pivot every column occur when A plus 1 is different from 0. So it means those vectors will form a basis when A is different than -1. Okay, so this particular problem, we don't have they do not form a basis for every A. They form a basis as long as A is different from -1, and then they form a basis. All right. Now, another way you could answer this question and is the following. you can use the idea of determinant, because when I gave this exam last year, or that's actually this exam 2 years ago, determinant was not covered. So another way you could have solved this problem is say, okay, those are 3 vectors. They are linearly independent if their determinant is non-zero. So you can compute the determinant. I won't, you guys do it yourself. So you compute the determinant and you find the value of A such that the determinant is different from 0. And if you do that, you will get exactly the determinant is different from 0 when A plus 1, not 0. It means A different from -1. Check it and make sure you get the same answer. So you could answer that 2 ways. Either you proceed as I did, or you can check the determinant. Now, what's the benefit of both of them? You can use the determinant idea only if you have 3 vectors in R3, 4 vectors in R4, which is what we have in this scenario. But if you are in a different scenario, not basis, in totally different, in another scenario, and you have, let us say, 2, 3 vectors in R4, so you have 3 vectors in R4, then you cannot use the idea of determinant because we don't talk about the determinant of a 3x4 matrix, of a 4x3 matrix. So if you have 3 vectors in R4 and you have A, and you ask for which A you have the vector linearly independent, you have definitely to proceed like that. If you have 4 vectors in R4, and then you can use the idea of a determinant. So that's why this is absolutely crucial, because we don't always have the number of vectors is not always equal to the number of entries in each vectors. Right. So this is basis for R3, and I repeat, go over the lecture I did about basis very well again. And so what else do we have? So this take care of a basis, and then you have the null space and determinant. We covered it already. So the null space, it means all the vectors such that AX equal to 0. So you have to know the definition. So you know how to show that the vector is in the null and how to show the vector is not in the null. So the null space are all the vectors where AX equal to 0. And finding a basis for the null is actually simple. You just have to solve the system AX equal to 0 and write the solution in parametric vector form. So I will go again through, I think I have a problem in here. Yeah. So for example, let A be a matrix. And then I usually, when I give you this problem, I give you the echelon form of the matrix because it's usually tedious. And the question is, find the basis and give me the dimension, even though I didn't ask it here. Okay, find the basis. It means you need to find vectors in the null, which are linearly independent, and they cover the null. It means everything in the null is their linear combination. So the only way we have to do it, we have to solve it. The null is all the x's in R5 such that AX equal to 0. We have to solve AX equal to 0. Now, since I gave you the echelon form, you just solve it. And then you have to write the solution parametric vector form. So here I have 2 free variables. I have x2 and x4 free. And then the first row will give me this equation. That's the second row. So what I will do, I set x2 equal s, x4 equal to t, and I write the solution in parametric vector form, the way we've done at the beginning of the semester. And now we analyze this. What does this tell me? It means that any vector in the null is a linear combination of those 2 vectors. It means any vector I put here. Remember, first here, those vectors have to have 5 components because I have 5 rows here. Any vector I put here that make A times X equal to 0 is a combination of those 2. So I already understand fully the solution set of the system. So the null is the span of those 2 vectors because anything in the vector linear combination. Moreover, if you just look at those vectors, they are linearly independent. And usually all the time, when you write the solution in parametric vector form, even if I have a third vector here, which is why not, they will be linearly independent. And that's really a theorem that we can show. So this tells me that the basis, so those are 2 vectors, they cover the null, which is a subspace. They are linearly independent. So it means that the basis for the null are exactly those 2 vectors. Okay. Right. So that will a little bit give you an idea about the null. and then we covered the determinant. All right, so this is my review. That's my review. I gave you 2 quizzes which are relevant to this exam, but it has to deal more, if my memory is right, with the algebra of matrices. So please go over the quizzes, go over the homework, go over that. And if you have any questions, you can email me and then I will answer you through the email. Okay, good luck. And that's the end of my review. If you have questions, as I said, please email me. Bye-bye. Good luck.